silicon frame grabber with a scope probe hooked onto an internal test point that's generating a TTL trigger signal. That trigger signal is then converted to a CoaXPress trigger packet, sent up the cable, because at the same time as high-speed data from the cameras come the other way. At the other end of the cable up here, the trigger goes into the camera, it decodes the CoaXPress packets, and then generates a TTL trigger out on a test point at the top of the camera. And this scope probe is hooked onto there. So if we go to the oscilloscope, on the blue trace we can see the TTL signal in our frame grabber. On the purple trace is the signal in the camera, and the scope is showing there's a 3.66 microsecond delay between the two, and that is a fixed latency. And that's basically about 3 or 4 characters of the low-speed link. But what's very clever is that there is a timer in this CoaXPress spec that times between when the trigger event happens. So if your trigger happens here, which is midway through one low-speed character, there's a counter then runs and counts high-speed clocks all the way to the next packet edge. And that number gets sent down the link so the camera can receive that count, load into its own counter and recreate the trigger pulse in the correct offset from the packet boundary. So if I zoom in on the purple trace to jitter, this is on 4 nanoseconds per box on the oscilloscope. We're only here about 4, 8, 10, 11 nanoseconds jitter. But that could actually be half that in the spec, because this implementation we are running is only using a 125 megahertz clock. The specification allows a 250 megahertz clock, so that jitter theoretically can be half that in a real application. So the key point is, while we have a fixed latency of a few microseconds, we can recreate a trigger pulse or a camera exposure pulse with a tiny jitter at the other end. So hopefully that is clear.